When a loggerhead sea turtle hatches on a beach, it scrambles into the surf and disappears into the Atlantic. For years, that single turtle will traverse thousands of miles of open ocean, navigating one of the vastest environments on Earth. Decades later, that turtle will return to reproduce. A mature loggerhead bypasses thousands of miles of suitable coastline to return to the specific stretch of sand where its life began. Biologists call this natal homing. To explain having managed this precision after decades at sea, scientists proposed what's known as the geomagnetic imprinting hypothesis. The theory suggests that before a hatchling ever leaves the beach, it memorizes the specific, localized magnetic signature of its birth environment. The system relies on two primary data points. The first is the inclination angle, the specific slope at which magnetic field lines intersect the Earth's surface. The second component is field intensity. Together, these two measurements intersect to form a unique biological coordinate on a global magnetic grid. Proving this requires demonstrating that an animal successfully relies on an invisible set of coordinates to cross the ocean over a 20-year lifespan. Testing this directly presents a severe physical problem. You cannot attach a tracker to a hatchling and expect it to stay operational for 2 decades until the turtle reaches sexual maturity. Since researchers could not track the turtles over that timescale, they needed a natural experiment. Instead of tracking the animals, they decided to track the Earth's magnetic field. The eastern coast of Florida contains the largest loggerhead rookery in North America. Biologists maintained a 19-year, highly detailed database recording exactly where these loggerheads nested across 12 different Florida counties. Buried in this data was an unexplained anomaly. In certain years, the density of nests in one county would sharply increase, while right next door, the nesting density would drop during that exact same period. The independent variable driving this anomaly is a geophysical phenomenon known as secular variation. The Earth's magnetic field is dynamic. The specific magnetic coordinates across the globe gradually shift and warp over time. If researchers could match the shifting magnetic anomalies along the coast with the spikes and drops in turtle nesting, they could establish a statistically rigorous proof of magnetic navigation, solving a decades-old mystery without ever attaching a single physical tracker. Florida's geography is uniquely suited for this test. The coastline runs north to south, while the Earth's magnetic isolines generally run east to west. Looking at this map, we see how specific inclination isolines cross the Florida coast, creating distinct stacked latitudinal signatures. Because of secular variation, these magnetic stripes are not permanently anchored to the bedrock. Over the past 2 decades, these isolines have slowly drifted northward. The exact magnetic signature a female turtle imprinted on as a hatchling has physically moved up the coastline by the time she returns. A turtle navigating purely by physical geography will return to the exact same pile of sand. A turtle following a magnetic map will nest in a new location, tracking her specific imprinted coordinate as it moves. Secular variation physically separates geographic coordinates from magnetic coordinates, allowing scientists to test which mapping system the turtles are actually using. To track this drift, researchers developed an objective mathematical metric called the convergence index. Imagine a clean stretch of vertical coastline, intersected by 2 horizontal magnetic isolines. We have a fixed population of turtles that hatched in the space between these 2 lines, imprinting on that specific magnetic zone. Over 20 years, both isolines shift northward due to secular variation. If the bottom line moves faster than the top line, the 2 lines physically move closer together. The magnetic signatures between those lines are now compressed into a much shorter stretch of physical beach. When those turtles return, they seek out their imprinted signatures. Because that magnetic zone has shrunk, the turtles are forced into a smaller area, mechanically driving up the number of nests per kilometer. Conversely, in a scenario of divergence, the isolines spread apart, stretching the magnetic signatures over a longer stretch of coast. Returning turtles spread out to match, and the local nesting density drops. If the geomagnetic imprinting hypothesis holds true, the spatial changes in Florida's sea turtle nests must rigidly obey this convergence index. This bar graph displays results from the 19-year database. In coastal areas where isolines converged, nesting density increased by 35%. Where isolines diverged, density decreased by 6%. This shift is highly significant, unlikely to be random population variance. This scatter plot measures the exact correlation between isoline movement and density change, mapped onto a linear mixed effects model. The regression line confirms a strict relationship. The highest rates of magnetic convergence are associated with the greatest increases in nesting density. This trend is mathematically consistent across all 12 individual coastal counties tested in the study. The regression model identifies the mechanism behind these nesting shifts. Turtles are tracking dynamic magnetic targets as they drift along the coastline. This data does not imply that every individual turtle possesses a flawless internal GPS. What we are looking at is a population-level distribution. Individual turtles actually make considerable navigational errors. They often miss their exact magnetic target by varying distances. Through a phenomenon resembling the wisdom of the crowd, these individual errors cancel out. As a collective, the peak of the population's overall nesting distribution stays tightly coupled to the moving magnetic signature. Magnetic imprinting operates as a macro navigation tool. It provides the mechanism required to cross an ocean basin and arrive in the general coastal vicinity. Once they arrive in that vicinity, local environmental cues like sand quality, beach topography, and visual markers take over for the final nest site selection. By identifying a slow, invisible geophysical anomaly, researchers demonstrated how a complex migratory map operates over decades, bypassing the need to track individual animals.